Hey guys, in this video we're going to be talking about about pKa and its relationship to acid-base strength. You can see in this definition here, pKa is equal to the negative log of Ka, where Ka is defined as the acidity constant, right? If you remember from general chemistry, when we're talking about Ka, what it's really saying is that it sort of defines the strength of an acid by the extent of its ionization in water. Right, so we have our conjugate base, our acid, conjugate acid, and our base. And Ka up here is what sort of tells us, okay, this is the acid dissociation constant, right? And the value indicates the relative strength of the acid. The stronger the acid, the more it dissociates, giving it a larger value of Ka. But we won't, we're not going to be too concerned about the math, but that is where that number is coming from, right? And pKa, taking the negative log of it, just gives us a better number to work with rather than a number in the tens of thousands or whatever. pKa just keeps it in a short range, typically anywhere between -10 and 50, right? So it's giving us a better number range to work with, right? That's all it means. So the general rules for pKa is if you have a strong acid, right, the pKa will be less than 0, right? And if you have a strong acid and you take away the proton, it becomes a weak conjugate base. And if you take a weak acid, right, that weak acid is typically anything with a pKa over 0. If your weak acid has its proton taken away, it becomes a strong conjugate base. Okay, and we'll get plenty of examples of that down the road. But essentially, the stronger acid a molecule is, the weaker the conjugate base will be, and vice versa. So we'll take a look at these following molecules down here, right? Looking just at the pKa, we can tell if it's going to be a strong acid or a strong base. Or, sorry, you can tell if it's going to be a strong acid or a weak acid. Right, we have this strong acid here, right, as a pK of -10, that is less than 0, so we know this is a strong acid. Right, and if we got its conjugate base, it would be a weak conjugate base. Okay, this one right here, it's close to 0, but it's still over 0, so we know this is a weak acid. Let's see, the next one, this is well over 0, so we know this is a weak acid. And this final one, right, we have our carbon-carbon molecule. We know that these sort of organic molecules like this are very, very weak acids. So you would even say this is a very weak acid. You need a very strong base to be able to deprotonate, right, this proton, to put a negative charge on carbon. Typically, right, the pKa of water is about 16, and any molecule with a higher pKa typically acts as a base, and any molecule with a lower pKa typically acts as an acid. And we can kind of see that here with nitrogen, right, where it has that lone pair, where it can do, right, it can act as a Lewis base and donate electrons, right? So this will typically act as a base. So here I just have like a short list of pKa's I've generated. And in the next video, we'll be going through why some of these molecules have the pKa's they do, right? So we can look at why does this compound, with 3 fluorines, have a lower pKa? Why is it more acidic than this compound up here, which looks almost exactly the same, except for it doesn't have 3 fluorines on this carbon, right? So we're going to start comparing some of these molecules and saying, okay, why is one more acidic than the other? So we'll go through some of these examples in class, but what I want you to do is, using the chart right here, approximate what the pKa values for each of these molecules are going to be, right? They're not going to fit exactly on the chart, But do your best to look at the chart and see which one fits. And that'll give us a general idea of the pKa of each of these molecules, right? It doesn't have to be perfect, right? You can say approximately this pKa for this molecule, and we'll go through during class and sort of take a finer look at some of these molecules and their pKa's.